So in this reaction, we have the formation of gaseous hydrogen fluoride from hydrogen and fluorine gas. This reaction has an equilibrium constant of 1.15 times 10 to the second at a certain temperature. So that's our Kc value. In a particular experiment, 3 moles of each component was added to 1.5 liter flask. So these are my initial values, and they would like for me to calculate the equilibrium concentrations of all species. And so I'm given initial values. They're asking me to solve for equilibrium values. This is a nice chart problem. Like all problems, it starts with a balanced chemical equation, and then we're going to set up our ICE. Then I'm going to plug in the information given to me in the problem. They gave me initial values for each chemical species. Each one is 3 moles, and they're all inside of a 1.5 liter flask. So I do have to calculate the molarity by doing 3 moles over 1.5 liters for each one. So the initial molarity of everything, let's say with hydrogen, for example, is 3 over 1.5, and that is 2 molar for each one. Next, for the change row, we have to use coefficients here. We have to use x's here, but we have to know in which direction the system will proceed to establish equilibrium. I don't have any zeros in my initial row, so that indicates to me that I'm going to need to calculate Q. So we're going to calculate Q, or more specifically QC, set it up by writing the QC expression first, and then sub in your initial values. Don't forget that your coefficients become exponents in a QC expression. And so now I'm going to grab the initial values and plug them in here to our QC. So plugging in our initial values, we see we're going to get a QC value of 1. The next step is then to compare Q to K. Kc was given to me in the problem. It is 1.15 times 10 to the second, and then the QC we just calculated as being 1. So we can see here that Kc is greater than QC. So I think to myself, okay, well then that means we're not in equilibrium, but the system will proceed in a direction so that Q will eventually equal K. So Q must increase here. So therefore, we're going to need to make more product. That means the system is going to proceed in a forward direction or to the right in order to establish equilibrium. So we're moving in the forward to the right towards the product. Back to my ICE chart. Now know we are moving in the forward direction. So for my change row, minus 1x for the hydrogen, minus 1x for the fluorine, plus 2x for the HF. Paying close attention to the fact that we're moving forward, so we have to add to the product side, subtract from the reactant side. And then also remember the coefficients from the balance equations, carry them down. They're going to be the coefficients in your change row. So because the hydrogen fluoride has a coefficient of 2, it's going to be plus 2x on that change row. Then your equilibrium row, in terms of x, combine the initial and the change rows. Then for the last row, the equilibrium in terms of molarity, remember these two last rows are always equal to one another. And so I go back to the problem. Did they give me any equilibrium concentrations for any of the chemical species? And the answer is no. They didn't tell me any of the equilibrium concentration. So I can't really use that method where we're going to set the first E equal to the second E. So I have to think of another way in which we're able to solve for X. And that other way is by using the Kc value. It starts by writing the correct Kc expression and then plugging in the value of Kc. And then plug in the equilibrium concentrations of all your species in terms of X. So go back to your ice chart, look at your equilibrium in terms of X. These are the values that you're going to plug into the Kc expression. Okay, so we subbed in and we get our new equation here, and we notice that we have a perfect square on the top, and then on the bottom I also have a perfect square. That quantity of 2 minus x is going to be a perfect square because I can rewrite it like this. And then to solve for x, because I got those perfect squares on the right hand side of the equation, let's take the square root of both sides. After I take the square root, we're going to want to cross multiply and then solve for x. So x is equal to 1.5284 molar. We're now going to take this value and you're going to sub back into that ICEE chart. And then you'll have your equilibrium concentrations for all the chemical species. So I've just subbed in X for all my chemical species at equilibrium. So I'm just highlighting that value of X that we just solved for. Just keep in mind though, for this product, it is 2x, so don't forget to multiply by 2. And then last part, finish calculating. So there you have your equilibrium concentrations of all your chemical species in this system. Just to make it real clear though, let's go ahead and rewrite it. So at equilibrium, the concentration of hydrogen and fluorine are both 0.472 molar, and the concentration of hydrogen fluoride is 5.06 molar. Now, some things to note conceptually here is that the concentrations of hydrogen and fluorine at equilibrium are equal to one another, and that's because, looking at your ice chart, they both start with the same molarity, and they both have the coefficient, so they're going to be consumed in the same ratio. That's just something very conceptual to note, that these two have the same initial conditions. They both have the same coefficient, so they're both going to have the same equilibrium values. And overall, their concentration is decreasing from start to equilibrium because the reaction is moving in the forward direction. We are going to use some of those reactants to make some more product. So if I look at our product here, we should see that the amount of product has increased from initial to the equilibrium, because in order to establish equilibrium, this system had to proceed in the forward direction.